We mentioned before Ohm's law. Now let's go into deep inside to see how we actually use it in order to calculate different parameters in electronic circuits. So first of all, let's define it. And again, as we've done before, I will read it with you, and then we'll talk about it in depth. The definition of Ohm's law. Ohm's law states that the current through a conductor between 2 points is directly proportional to the potential difference across the 2 points. I is the current through a conductor in units of amperes. V is the potential difference measured across the conductor in units of volts, and R is the resistance of the conductor in units of ohms. And we mentioned just a minute ago that it is directly proportional. And look at the graph. We have the vertical axis, the current, the horizontal axis is the voltage, and we have a linear graph. This linear graph is the resistance. Resistance is the voltage over the current. That's Ohm's law. And the very basic equivalent circuit to represent Ohm's law is having a voltage source, let's call it a battery, that through a resistor current flows. So we have one voltage source, one resistor, and one single current in this circuit. And we have what we call the Ohm's law triangle, where we have V on the bottom, V on the top inside the triangular, V, I, and R, and we can see the relationship between the volts, the resistance, and the current. V equal I times R. If we want to find I, we take the voltage, we divide it by resistors. We want to resistor, we take the voltage divided by the current. In each case, basically, it's the same formula. It just depends what we want to find, given that we have the other two. And there is an example on the bottom. If we have 10 volts across a resistor, and the resistor is 100 ohm, that means that it's 10 over 100 is basically 100 milliamps. So in this particular case, we apply the formula of the I equal to V over R. So that's Ohm's law. Here are 3 examples of Ohm's law. Schematic A, a battery, 10 kilo ohm resistor. So it's 10 volt divided by 10,000 ohms. Basically, if we divide it one by the other, we will get 1 milliamp. 1 milliamp is 1/1000th of an amp. Example B, we have 2 resistors. Each of them is 1 kilo ohm. We know by now that we have to add up the resistance of both resistors, so it's 10 kilo ohm in series to another 10 kilo ohm. The equivalent resistance is 20 kilo ohm. We do 10 volt divided by 20,000 ohms, 20 kilo ohms, 20,000 ohms. We come out with 0.5 milliamps. Example C, we have 2 resistors in parallel. Each of them is 10 kilo. That means the equivalent resistance is 5 kilo. So we do 10 volts divided by 5,000 ohms, we will get 2 milliamps coming out and coming back to the battery. Now, because the 2 resistors are in parallel and they are identical, these 2 amps will be splitted in 2 halves exactly. 50% will go to branch number 1 and 50% will go to branch number 2. And we can see 1 milliamp goes to the right resistor and 1 milliamp will go to the left resistor in parallel. 2 milliamps coming in, 2 milliamps coming out. And here is another example. We have on the left-hand side, one series, one path. 6 volt battery goes through 2 set of resistors, 1 ohm each. So V equals 6 volt. the RT equal 1 plus 1 equal 2 ohm. So the current is 6 divided by 2 equal 3 amps. On the right hand side, the parallel. V equals 6, R1 equal 1 ohm, so I1 equal 6 divided by 1, so it's I1 is 6 amps. Same thing with I2 equals 6 amps. So the current that goes out of the battery is 6 plus 6, I1 plus I2, to make up the total current which the battery actually generates. So it's 6 plus 6 equals 12. And the equivalent resistance, because it's 1 and 1 in parallel, it will be 0.5 ohm. We can go through the example here. It's a little bit more kind of detailed, but again, if we will go through the computation, you can do it basically on your free time. Go to the formula, you will see the addition of the voltage drops across the series transistors. Divided it by the current to get the voltage, divide the voltage to get the current, play with the Ohm's law in order to get all the parameters of the circuit. And I want to put an emphasis just for 1 second that easily, once we calculate the one single current in this particular circuitry, we can calculate the voltage drop on each resistor. It's that current times the resistance to give us the voltage drop on that particular one. The summation of all the voltage drops is equal to the voltage of the battery. So let's now look at the power. This is an extension of the Ohm's law. The power basically is, if you look out to the bottom of the slide, P, the power is equal to the current times the voltage. And because voltage is itself, based on Ohm's law, is current times resistance, so we can actually look at this as the current square times the resistance. So if we do have a circuitry that has a battery, it has a current, has an equivalent resistance, we can look at the power. Now this power, and we will look very in depth about that particular power. This power in this particular case is a dissipation power. It dissipates by means of heat. The current that goes through the resistors heat up the resistor, and the energy is converted to heat and dissipate outside to the free air. The very basic one, look. We have the very basic circuit on the left, P equal V times I. Also, you can look at it as V square over R. And in addition, like we've seen before, I square times R. All these formulas are identical. Depends which parameter you have a value for it, so you plug in the value into the formula, and when you do not, you're fine. And here we have an example, just simple example on the bottom. And we have 20 volts battery connected in parallel with an 8 ohm resistor. The power will be 50 watts because it's utilizing the formula V square over R. V square is 20 times 20 equal 400 divided by 8, P equal 50 watts. Now, when we calculate the watts, which are the units of the power, we can calculate the watts per component. Let's look at the picture of the left. We have a parallel connected resistors, R1 and R2, 6 ohm R1 and R2 is equal to 2 ohms. And now that we know all the formulas and how to manipulate and play with Ohm's law, we can see that P1, the power dissipation that is being generated on R1, is P1 equals 12 volts times 2 amps equal 24 watts. Now remember, the 6 ohm resistor dissipates 24 watts by means of heat. heat that goes up to the free air. Now let's look at the R2, which is the resistor in parallel. It's 1/3 in its resistance, 2 ohm versus 6 ohm. And it's 12 volts times 6 amps, 6 amps because the lower the resistance, the higher the current. The higher the current, I square R is a bigger multiplication. This is why in this branch we get 72 watts. Now this 72 watts is 3 times more than the 24 watts before because the resistance is 3 times too little. So we take these 24 watts together with the 72 watts, we add up the two power dissipations, we get basically the same as the voltage of the battery, 12 volt, times the total current of the circuit, 8 amps. So it's 12 times 8 is equal to 96. 24 plus 72 equal 96. That's on the circuit on the left. Now let's look at the circuit on the right. Same battery, 12 volts. Now we have two resistors in series. Same resistor, 6 ohm and 2 ohm. Now because we have 6 and 2 in series, we add up the resistance, and 6 plus 2, the equivalent total resistance of the circuit on the right is 8 ohm. And if we have 12 volts, the source, and equivalent resistance of 8, the current is Ohm's law. V over R, the current is 1.5 amps. And when it's I 0.5 amps, P1, the power dissipation that is being generated because of the current goes through R1 equal to 9 volts times the current 1.5 equal to only 13.5 watts. And the current that the power dissipation that goes on R2, because R2 is 1/3 of R1 and the current is the same current. Remember, we are in serial connection. It's one loop. Current going in is exactly to the current, identical to the current going out. So it's P2 equal 3 volt times 1.5 times 4 equal 4.5 watts. So the voltage drop on the R2 is I times R, and the P is V times I, 4.5 watts. Same components, different connection configuration. See how much less power is dissipated from the serial example as compared to the parallel example. And this is a summary of the Ohm's law. And we have a circle here divided into 4 quadrants. The voltage quadrant, E, by the way, is same as U, same as V. We have a quadrant for the power, quadrant for the current, a quadrant for the resistance. This is a summary of all the different formulas all under the umbrella of the Ohm's law. We've covered them all. There is no need for me to go to every single section of it and describe. You can choose whatever formula that is more convenient to you based on the values that you have in your hands, based on the components that you have in order to find the end result.